For those who don't know me, my name is Jesse. I'm the Deputy Director here at BioCAT, and these days responsible for most of the SAXS program with the new hire, Max. He's going to transition into taking on most of that. And so what I want to do is I want to just provide a brief overview of kind of what the APS-U is going to do for the SAXS side of things, and also some other developments we have kind of planned and recently implemented to improve the program. So this is just a refresher on the numbers that Tom had provided. I'm not going to go through in detail, but Tom provided some overall numbers for the beamline. Of course, for any of our given experiments, we usually have to cut the beam down a little bit, collimate a little bit. And so, the realities on the ground are maybe a little different. For equilibrium SAXS, we're actually looking at maybe a kind of 6-fold increase in flux because we currently have to cut out a decent amount of the horizontal beam to pass our experimental capillary. And similarly, the same thing in the flux density. We maintain the same collimated beam size, but get more flux through it. For time-resolved SAXS, we expect a pretty large increase in flux density, maybe 25-fold, possibly more, in part due to the much smaller beam size, and in part due to just an overall increase in the flux because of how much we can accept on our microbeam optics. It may also be the case that we can use the main optics for our microbeam experiments. It's a little unclear. Tom's numbers were slightly more optimistic on the final beam size after APS-U than mine, so we'll have to see how it all works out. But either way, we're looking at fairly significant increases for both the equilibrium and the time-resolved program in terms of flux and significant decreases in the beam size. So there's several benefits that come from this. The most obvious, of course, is if we have more total photons or more total photons in the beam footprints, we're going to get better signal to noise. The APS-U promises to have improved beam stability, and so we expect this will generate kind of more reliable baselines for the SAXS program. For the equilibrium SAXS, the smaller focus at the detector should also let us reduce the beam size we're using, or beam stop size we're using, which will let us get to a lower minimum Q. I'm guessing optimistically somewhere around maybe 0.015 inverse angstroms, which is kind of 2-fold better than what we're currently doing. For time-resolved SAXS, we have a smaller beam will let us kind of push to earlier first time points with some changes to the overall mixer design. And the improved signal to noise ought to let us reduce sample consumption, which is pretty significant for especially the very fast time points. You can use a lot of protein to get the measurement that you're interested in. Now, for those of you who do SAXS and do it frequently, you probably recognize that an increase in flux density poses some challenges. So I do want to acknowledge those. And the foremost challenge for us is really radiation damage. Right, anytime you increase the flux density of your system, you have a greater chance of radiation damage to the sample. Fortunately, in our case, what we already have in place is this co-flow cell. So this sets up basically a co-flowing sheath of buffer around the outside of the sample as it goes through the capillary. And so this has been explicitly designed to prevent radiation damage in the sample. And using this co-flow geometry, which was developed at the Australian SAXS wax beamline, Nigel Kirby, who runs that beamline, has tested it with up to kind of 10 times greater flux and flux density than what we're going to have after the upgrade. And he was able to actually still collect reasonable SAXS data. So we're, let's say, cautiously optimistic or relatively confident that we'll be able to utilize more or less all of the beam that's available after the upgrade for our SAXS experiments. There are certain buffers that are particularly radiation sensitive that we may need to add some radical scavengers to, but I don't think it'll be anything over the top. I think the challenge for us is going to come in the time-resolved experiments where we have this radically increased flux density. And so, there's a few approaches we can take. We can mitigate, time in the beam with faster scanning and flow. We can add radical scavengers, but there has also been work previously, and I have a citation down here for people who are interested, on building basically a co-flow mixer. It isn't a unique idea. You basically add a sheath flow on the windows after the mixing zone, so you don't add in any extra mixing. And that, again, serves kind of the same mitigation purpose. So it may be that we'll have to take this more radical redesign method. But I think the path forward is relatively clear there because it's already been done in cases like the mixers that we use. It becomes simply a kind of fabrication and reliability question, which is not trivial, but is feasible. So that being said about the APS-U, I want to now talk about a couple recent improvements to the SAXS program, and then some of the planned improvements we have going forward that are kind of independent of, but on the same timescale as the APS-U. So Wei Kong in his talk mentioned our new detector. I have an image there of it in action, or at least not in action, but on the beamline. So the larger area of this detector does give us a wider Q range. At the moment, we're getting out to a little over 0.4. We expect to get out to 0.5 after some geometry optimizations to how we're running the system. The smaller pixels also give us better sampling in the low Q region. And we had great luck with our previous Dectris Pilatus detector, so we expect that this new detector will give us kind of continued high reliability operation for the next 5 or more years. In the last 9 months or so, we've also transitioned to a smaller SAXS beam stop, which has allowed us to push our minimum Q down to about 0.03 inverse angstroms. And this has been accompanied by some optimization and kind of reducing parasitic scattering at the beamline. So we still have very good low Q even with this smaller beam stop. We also implemented a new automated processing pipeline. I'm not going to go into the details here, but I'm happy to discuss it if you're interested. For us, that was a fairly significant thing. A few other highlights that I want to mention from the last couple of years. We've added temperature control from about 5 to 50 C for both the SAXS and SECMOL SAXS system. We now have kind of routine ion exchange chromatography available, as well as the analysis tools to deal with that data set, which was previously the challenge. These days we've gotten in kind of built up the infrastructure to routinely deploy both our chaotic flow, which is kind of our traditional mixing approach for the really rapid time points, and our new, not really new, but our laminar flow mixer, which we hadn't used much before. And this lets you get from about a millisecond to 1.5 seconds in time after the reaction, with a sample equivalent to about an injection for a size exclusion SAXS measurement. So it's very minimal sample usage, which is nice. We've made some improvements to kind of the reliability of the operation at the time resolved SAXS setup as well, which again, I'm not going to kind of harp on, but I want to mention it there. So as Tom mentioned, right, we're going to be going down for about a year in terms of the user operations. And much as we might like to, we're not going to spend that entire time on a beach sipping Mai Tais, right? We're actually going to try to do some work during the time as well. So the main thing for us is that APS-U really provides a key opportunity to do some major upgrades that might otherwise take away from user experimental time. A lot of the systems we have here at the beamline have been in place and in operation reliably for the last 20 plus years, basically the lifetime of the beamline. So we're taking this dark period as an opportunity to upgrade our vacuum systems, upgrade our cryogenic systems, upgrade a bunch of our motor controllers, do some reworking of our back-end experiment control software, upgrade our networking. That may happen sooner. And also we're looking at some new designs and improvements to even the vacuum systems in the experimental hutch. And so these are all things that are kind of fairly major and intrusive developments for the most part. And so having this year to rebuild a bunch of the beamline is really key for us, I think, in ensuring another 20 plus years of excellent and reliable operation from BioCAT. So specifically for the SAXS program, we have a couple major kind of builds that we're thinking about. So the first thing that we're currently planning is building basically a new entirely custom FPLC system for our SEXAX. And the plan is to basically be able to fully integrate this into the beamline software, giving us kind of full automation for sample measurement and buffer changes. And so, you know, the eventual goal is to reach essentially fully unattended running for samples that, you know, we're confident don't require our inputs. We still intend to encourage, you know, run a user operation and user oversight, but there are certain cases where you have samples that are well behaved. You just want to queue them up overnight, go home, and come back. And so we're hoping that this system will enable, you know, rapid temperature changes, recovery, pausing and recovery of automated fashion from beam losses, things like that, to ensure that you get good quality data on every sample that you put in. That's the goal. We're also planning an upgrade to our batch mode capabilities. So for cases where you can't do SAXS for some reason, we're looking at developing an auto sampler that will load directly into the CoFlow cell with volumes as small as 10 microliters, and all the kind of radiation damage benefits that you get from CoFlow. And so here, we're looking to automate basically the use of 96 well plates and again, achieve kind of this fully unattended running of batch mode samples in the cases where that's appropriate. And so, I think many experiments benefit by having a user on site or a scientist on site providing the oversight, but it also does make it a little hard, especially in COVID times, where we had many fewer experimenters at the beamline, to make good use of all the experimental time, because our flesh is weak and we have to rest on occasion. And so these are kind of the major upgrades we're thinking about. There's a bunch of other small stuff as well, but we're really, we're disappointed, of course, that we will have a year where we can't run experiments for all of you, but we're really excited about the possibility of coming back with a bunch of new exciting capabilities and providing really excellent reliability and quality of data for the next however many years we get to operate here. So with that, I'm happy to take any questions. Or we can move on to Tom's talk.
Hey, Jesse, I can't resist asking, when you're going to do a custom system to replace your ACTA, are you going to use ACTA hardware, or are you going to use some different, or use a custom?
Because you can't really control the ACTA hardware from your own programs, right, Rachel? That's the problem, is you're locked into this proprietary infrastructure. So we've been putting a reasonable amount of effort into sourcing, high quality components that have that we can control directly, over serial or USB or whatever, and develop our own control systems for.
Yeah, I think it's
we
totally.
Want to be able to tightly couple.
Mm-hmm.